We're gonna skip Reza Farhan for now and move on to Chris Ferraro, who's gonna talk about municipal solid waste incinerated bottom ash. All right, thank you.
Thanks so much, Iho, and thank you all for attending this afternoon. So what I want to do today is go over some work we've been doing at the University of Florida, where we've been using MSWI bottom ash as an aerating agent. We've been using a number of recycling efforts for the last 10 or so years, or even 15, but this is one smaller project that we're currently working on. So real briefly, we've talked a lot about this, but when we think of residuals for use as a reuse application, we can have recycling products and we can also have reused products. And when we think about the potential for MSWI, it can be used as an aggregate, it can be used as a number of different components for concrete, and in this case, a little bit more of a specialized ingredient, and so I'm going to talk about that today. For those who are not familiar, the waste to energy process is just basically burning garbage, okay? And so we have our, urban or suburban household trash that gets put into a waste bunker that then winds up going into a boiler, into a furnace. Furnace powers the boiler, you get electricity out of that. And then there's all the stuff that we don't want are the residuals. The bottom ash, which is 80% of the total residual, so about 80% of all WTE residual is the bottom ash. There's also some waters that come with that. Those usually wind up right in the landfill. And then there's some fly ash as well. I'm not going to discuss most of what we're talking about other than bottom ash today, okay? And so looking at and focusing on the boiler for a minute, for the furnace for a minute, let's see what we really have when we look at that, right? So in there, we basically have just an controlled but uncontrolled in some levels. And it's not as controlled as a cement kiln, roughly 800 C burn. And so it's not as hot as a cement kiln either, so we're not getting complete combustion of all the materials in there. So when we're finished burning that, we get a residual that looks like basically very dirty, coarse aggregate, or even aggregate for concrete. And if we clean that stuff up and we look at our components, we have ceramics, we have concrete, we have glass, slags, ferrous metal, and non-ferrous metal. And for the purposes of this talk, I'm going to focus mostly on the non-ferrous metal, the aluminum. Okay, and so if we look at the elemental composition of waste energy ash, municipal solid waste incineration ash, we have some similarities and we have some differences. The aluminum content is the most important part with the bottom ash that we're looking at. We see that we have an elevated aluminum content in our residual. We also have a metallic aluminum content in our residual. That's very important. Chlorides are there, which is obviously a problem when we think of potential issues with rebar corrosion and so on. And then we have elevated alkalis. I'm not going to discuss the alkali portion today, but I didn't want to be silent on it either. Okay, so the percentage of aluminum MSWI bottom ash is about 3 to 15%, depending upon the source, depending on how good the non-ferrous metals removal is. Non-ferrous metals removal is becoming something more popular, so I expect this number to decrease over time. There's a large initiative throughout the US and especially in Europe to mine MSWI landfills and really just reclaim those elements. Basically, I consider it to be like a urban mine, a mine that is born from our waste materials. Okay, so what I want to do for a moment, and this is a little bit more of the material science portion of what I'm talking about today, is spend a little bit of time talking about the corrosion of aluminum, but not so much to put you to sleep, so we're going to skip some equations, but we have aluminum, we have an aqueous environment, and that will result in some hydrogen gas. When we get into our Portland cement environment, we obviously have elevated pH, we have calcium, and so on. And so skipping a number of equations, we see that we have, again, our metallic aluminum, our aqueous environment, and that turns into a corrosion product and the evolution of hydrogen gas. This is obviously the important part for what we're doing as we use it towards autoclaved aerated concrete. And this is just basically our final equation in that, we'll call it a brief derivation of hydrogen production from aluminum in MSWI. So when we first started looking at MSWI, we started blending, or really segregating it into a coarse fraction, which we call the greater than fraction, and a finer fraction. And so we used a 3/8 sieve and basically said, okay, everything bigger than that we'll keep, we'll use for concrete as a coarse aggregate. Everything less than that we really don't know what to do with. So our first step was, what do we actually do with this stuff? And part of the reason for that is I just talked about the hydrogen gas formation. If you look at the resultant concrete of the stuff on the left, That looks like normal concrete. That's using the greater than MSWI. When we use the less than, we saw a lot of hydrogen gas formation. And so you see bubbles, you see poor workmanship. It's just harder to use. So we're not going to use a fine MSWI in concrete production based on everything that I've experienced so far. We did do a case study where we built a road down in Pasco County out of that stuff. But again, we had to get rid of the less than stuff. So we have basically half of our MSWI ash not being reused. And that is, I think, one of the problems that born us into maybe we can reuse it in another way. So how do we upcycle this stuff? We know that 90% of the aluminum is in the less than fraction from research, and I'll show some data that also confirms that. And we know that while metallic aluminum in MSWI can damage OPC structures, if we can control that, it actually can make an aerated structure. And so that's what this research focuses on. So now let's talk about autoclave aerated concrete, which is not a typical concrete, obviously. And I'm just going to kind of take us through a production process very briefly. We see that we have our sand components and our cementitious components. Those wind up going into a mixer, and then we'll take our steel cage, or the manufacturer will take a steel cage, put that into the mold. That all winds up going into the mold, and then that all winds up going through a molding process and into an autoclave. Autoclave pressures and temperatures differ. Some are up to about 150 Fahrenheit, so we're 70 C, and the pressures vary up to roughly 200 PSI. I'm sorry, I can't immediately translate that in MPa. Advantage of this stuff, basically, it's a good construction material that's relatively light, has a decent compressive strength to it, about 5 MPa, so 500 PSI, somewhere in there. It's used for building homes. It can be used for a number of other things. It also has a decent aesthetic look to it. In our particular state, Florida, in the US, we have a 100-mile radius from one AAC producer. But one thing unique about Florida is we have 15 waste-to-energy plants. So we do a lot of waste-to-energy in Florida, more than most other states in the US. And so that gives us a little bit of an opportunity to use this stuff. Okay, and that Aircon site is the one just south of Orlando in Florida, and that's their production facility. They were gracious enough to let us visit and gave us a lot of pointers on how to make good AAC. All right, so now that we want to start combining those two, we've given you a background on AAC, we have a background on MSWI. Let's go ahead and combine those two and see what we get. So again, we know that MSWI contains aluminum. We know that it also has silica, and we also know that it has things that we want from our Portland cement: silica, calcium, and so on. It can be domestically produced. Prior research, we know that we can actually improve our airborne distribution, improve strength potentially, and reduce material costs. And the economics behind this is a long conversation we can have maybe after all the sessions end and have a beer over that, because I think one of the biggest barriers with anything is not just is it cheaper, but is the material consistency useful in a production scale? And I see this with MSWI and cement kiln feed. I see it with this product. I see it as an aggregate. So every time we go to use this stuff, there's someone on the specification side saying, can you give me something as consistent as what we get naturally mined stuff? And the answer is usually no, and that's the biggest barrier I've seen so far. Okay, so what do we look at when we see our typical mix design for AAC? We have basically sand that's ground up, some Portland cement, some lime, aluminum powder. And the aluminum powder is very reactive. When we went and visited that site, they have it in a bunker because it's basically explosive. It's so reactive, so they can't store it like you would normally store aluminum. So that in and of itself made me feel like, all right, maybe if we take some less reactive MSWI, it's easier to store and much safer to use. And then we'll also add some gypsum and anhydride. Our particular design is we obviously were replacing the aluminum with MSWI. So we had to increase the weight of that because the pure aluminum obviously has a lot more aluminum, where MSWI has a fraction of aluminum. So we were also able to replace some of the sand as well because that's present in the MSWI. So I'm going to give a very brief overview of the project we did and touch on some of the highlights. So our task 1 was chemical properties, task 2 is size reduction and hydrogen gas production rate, and then dry density and compressive strength. And I think I have one slide on the third task. So looking at chemical properties, again, we started focusing on the less than MSWI because we know that we can get rid of the greater than stuff. And so we got 2 sources in Florida, And we basically, one's an RDF and one's a mass burn. The mass burn facility tends to be the more popular facilities. All the new facilities coming online in the US and in Florida especially are mass burns. We have one RDF left, but we thought it would be incomplete research to not look at the RDF. And so we did some particle size distribution, we did some ICP. Particle size distribution was a little bit on the crude side. We did some sieves, and then we went ahead and pulverized that. When we look at our average size, we see that we're looking at, D50 of around, a millimeter. And more than 50% of that bottom ash is greater than that. And so poor Robbie there in the middle, one of my undergraduate students is basically doing a we'll call a hand hammer mill, and then we went ahead and put that in the pulverizer once it was small enough. If you do decide to work with this stuff and you have those mills, make sure you use the ceramic plates, because it'll tear your metal plates to shreds in one pass. One of the things that we found out that was pretty important, we feel, is that when you look at the less than size, we see that the majority of the aluminum is in the greater fraction of the less than material. So I split my 3/8, and I have most of the aluminum migrating in the number 4, 8, and 16 sieve. Okay, so if we were going to do more work and reduce that and really try and focus on the aluminum, that's where it resides. And again, that's a product of the non-ferrous removals at the particular waste to energy facility. That's going to change with more advanced metals, non-ferrous metals removal in the future. Sorry. Okay. And so we got our size reduction. We wanted to get into hydrogen gas production. And so we took our aluminum metal powder and basically worked on a comparative test where we did aluminum powder versus our MSWI. We did some solution alkalinity, and I can't get into the hydrogen test. I really would like to go into depth on that today, but we developed a test to measure our hydrogen and our hydrogen gas. Again, we have our smaller aluminum particles, and we have basically, I'm looking at, there's one that's an unpulverized, but we're looking at the finer fractions, so the stuff more towards the left side of our screen as far as the aluminum and its reactivity. And so when we go ahead and look at that, we have basically what is an expected line of aluminum gas production if we use a perfect equation. And then we have the stuff we're getting in the lab. And what we basically found out is we can measure all the aluminum or the hydrogen gas production produced from an aluminum source. Again, that's basically an experiment that collects the hydrogen gas formed in a liquid container that we've developed. So the red lines give us our expected, and we're about 5% error. I'm pretty happy with those numbers. And we realize that, another part of this is the gas generation has to be fast and exhausted within minutes of the reaction. And that's really important because our particle size of our aluminum has to be small enough that we get reactivity and hydrogen gas formation while the concrete's still plastic. Otherwise, we don't have anything useful. So that's obviously going to be a driving factor of workability and so on. Okay, so we did our trials to find the best production processes for AAC production, and I'm going to go over these very briefly. Basically, we steam cure for 48 hours in water-sealed containers. Then we go ahead and slice that portion off. So you already see there is some expansion in the molds, and this is the exact same process they have at the aircon facility. We just do it in the lab, much smaller. And so once they're demolded, we go ahead and preserve from the finish phase and the loading phases. That's our specimen production. That's our autoclave. So we put those into the 2 inch by 2 inch by 9 inch bars into the autoclave, let it go for 190 for 24 hours, and then we can scroll saw these and cut these into whatever sizes we want. What we did learn is the higher the water to solids improves bubble dispersion, which is kind of obvious. The more workability you have, the more we can get a better air dispersion, or in this case, a hydrogen dispersion. And then we have our typical AAC. So we worked with the manufacturer to get a typical AAC that's not using the MSWIs, and it worked in the lab just fine. Here's ours with our less than ash, and you can see it's a little darker. Basically the garbage is dirty, and so when we start looking at things like strength versus tri-density, I believe this is my last slide. We see that. If we look at our red line, there's a lot of data on here. We see our red line, that's basically what we have at the facility that they gave us, and then we try to do our best to match that line, and we can produce pretty good AAC using the MSWI ash, and we're working with manufacturers to try and bring that online, but again, we do run into the variability issue. How variable is your ash? And if it's giving us an aluminum content that changes even slightly, it's a big deal to them. So I don't think this is quite ready for real time. And with the summary, I have, the hydrogen gas rate is obviously sensitive to particle size. That's a very important part controlling all this. Aluminum concentrates in the 4 coarser size fractions. We can meet industry specs for air dry density, and the strength ratio is there. I want to acknowledge the Hinckley Center for Solid and Hazardous Waste Management for funding this research, Aircon, Pasco County, and our friends in Florida. And that's it. I don't know if we have time for questions or how maybe if we don't have, it's a quiet crowd, so I'm not too worried, All right, we'll save it for later.